Okay, so logistic regression predicts the probability that a sample belongs to a particular class. Okay, so the decision boundary that you had seen is basically a linear line that divides a sample space into two regions. So in principle, this is very similar to a linear regression model, but the response variable is binary in nature. Okay. On the other hand, predictions that are made by taking into consideration all the possible known outcomes to make final classification is what a decision tree model does. Okay, so this is a very simple to use model, easy to understand model. And the nice thing about this model is that it can handle any kind of predictive variables, be it continuous numeric, discrete numeric, categorical, Boolean. So that is not the case with logistic regression. So, and also this model is scale invariant. That means you don't have to think about scaling all the predictive variables to the same level because this model handles each predictor at a time. That's the beauty of the model. So to predict whether any particular sample out of the sample belongs to any of these conditions, we can use such a decision tree model. So typically here you ask a question which can create splitting of the data, such as the question here is whether my out of the sample still grid belongs to any of the following conditions numbered as 2, 3, 6, 7, 8, 9, and so on. If yes, then what? If no, then what? So this then branches into several different internal nodes. So the initial node is what we call as the root node. And this again branches into an internal node where you further ask questions such as whether my carbon percentage or sulfur percentage is greater than a certain value or less than a certain value. So you keep doing the splitting over and over again till you get internal nodes, resulting internal nodes, which are as homogeneous as possible. So it should have maximum number of one particular class. Okay, that should be the objective. So to branch out to more and more internal nodes so as to increase the homogeneity. Okay, so just give me a second. Okay, so now the homogeneity or heterogeneity of a node is what is measured by something called as a Gini impurity. So the Gini impurity is empirically given as 1 minus summation pi square. By the way, can I take a 5 minutes break? Is that okay with? I was discussing about the decision tree model. So we were up to this Gini impurity, and the calculation for Gini impurity, the empirical form of this Gini impurity is 1 minus summation of pi square. P stands for the probability. I'll explain that shortly. So Gini impurity measures the heterogeneity of a node. More is the heterogeneity of the node, higher is the Gini impurity. So if we were to choose, say, two different elements from a set of two different heterogeneity, then the one that has a higher heterogeneity will have most of the time non-identical elements in its pair. Okay, and also the probability that one particular combination or one particular pair will appear more than once is the least in case of a highly heterogeneous system. While for a lesser heterogeneous or a more homogeneous, when you choose two elements in pair, most of the time you will have an identical element, okay? And also the probability that one particular combination appears more than once is also high, okay? Therefore, you can see this probability value for a highly heterogeneous system to have a particular combination appearing more than once is the least. So if you take the square of such probability values, it is going to be further less. And when you add all these probability squares together for all these different combination or corresponding to each of this combination, then the sum total of the probability square is also going to be very, very less. And when you subtract that from 1, and that is exactly what Gini impurity says, when you're subtracting it from 1, the resulting or the resultant is going to be a number which is very close to 1. Therefore, highly heterogeneous system will always show up with a higher Gini impurity. Is that okay? I mean, impurity value very close to 1. When doing a splitting, we have to take a few things in consideration. That is the weighted average of the Gini impurities of all the nodes. Weighted average of the Gini impurities of all the nodes originating from a parent node must be less than the Gini impurity of the parent node. That is what is explained here. Okay. So, like Gini impurity, you have one more parameter which is called as the entropy. Now, unlike the entropy that you have studied in thermodynamics, which measures the disorderness of a system, which could be a structural disorder or you say it could be a configurational disorder. In case of statistics, the entropy that we say is also Shannon entropy, that measures the variability of the data in a system. So it is one kind of disorderness, but it is more on the variability of the data. So entropy and gene impurity almost go same and same, okay, but their calculations are very different. So if you see the expression itself, in the entropy you have a logarithmic term, where while the gene impurity has a summation term. So when you are calculating the gene impurity and the entropy for the same range of probability, the gene impurity can go to a maximum of 0.5 and the entropy can go to a maximum of 1. So you can see the variation of entropy is much more than the gene impurity, and that is one reason why it takes more computational time and uh, processing requirement, computational processing requirement when calculating entropy. Now, when you do build up a model using Python and R, we usually avoid entropy because it is going to consume a lot of time. So we are happy with going with Gini impurity. Okay. Now, this difference between the Gini impurity of the parent node and the Gini impurity or the weighted Gini impurity of the child nodes is what we call as the information gain. So information gain is similar to something in thermodynamics which we have studied as free energy or Gibbs free energy. Okay, not exactly the same, but it can be somewhere correlated with the Gini impurity, with the Gibbs free energy. Okay, so you can calculate this information gain with respect to the entropy also, but larger practice is to use Gini impurity for calculating this information gain. Okay, now you can keep planting or you can keep growing the trees by adding more and more splitting criterion to all your nodes, or what we call as the internal nodes. But that is again not always a good practice. So I'll come to that again. So at each split, as I told you earlier, two things are same. One is that the Gini impurity of each child node or the resulting node must be less than the Gini impurity of the previous node or the parent node. And also, if one of these internal nodes of the child node has a Gini impurity value higher than the Gini impurity of the parent node, then that particular node is eliminated from the decision tree. It is not kept. And this, as I told you before, this difference, what we calculate between the Gini impurity of the parent node and the internal node or the child node is called as the information gain. So our practice is to increase or maximize this information gain. So if you are able to maximize this information gain, only then you can say you have done a good splitting criterion. Okay. Now, as I was telling you earlier, we can keep growing the trees by adding more and more splitting criterion. But again, this is not a good practice because too much overgrown trees can lead to, again, overfitting. And remember, decision trees are very prone to overfitting. There are ways we can minimize this overfitting by using a method called pruning. But this is, again, not covered in this particular session here. Okay, so what we saw then was that we increase the depth of the tree. Okay, now increasing the depth of the tree eventually led to an increase in the AUC of the training data. But when testing on the test data, it didn't show any significant change in the AUC. So we terminated our tree to grow to a maximum depth of 7. Now using 7 as the maximum depth, when we calculated the accuracy, it came out to be 76%. Now this accuracy is not too good as compared to logistic regression model, which gave me 87% accurate model. Now, why this low accuracy? One reason is there are many hidden overfitting. You cannot completely get rid of overfitting in a decision tree. So that is one of the disadvantage, but still I'll show you why it is good at some point. So that is all about decision tree.